So we're going to continue on in probability in chapter 9, but look at multi-stage experiments, independent events, conditional probability, and different modeling games. So a tree diagram is an often underutilized concept within probability because it can be quite tedious. So when you're doing a tree diagram, you're basically creating all possible outcomes for something that would occur, such as a spinner. If we're looking at this spinner, the first spin could be yellow, red, or blue. So we have a 1 in 3 chance of getting blue, 1 in 3 of red, 1 in 3 of yellow. But the second spin could then be blue, red, or yellow again. And so we start branching out into this tree where I could have a blue, then a blue, a blue, then a red, a blue, then a yellow. Or I could have a red, then a blue, a red, then a red, a red, then a yellow. And so I create this little outcome column here on the right-hand side, looking at those tree probabilities. If I look at those outcomes, I can then write my sample space out, and I've got a nice visual look at what that sample space would be. So the probability of each one of those outcomes happening would be 1 out of 9, because there's 9 possible outcomes, and the probability of one of them happening would be 1. Alternatively, we could also generate a table sample space. This is used far less, but sometimes it makes more sense to students because I have a B, then a B, a Y, then a B, a R, then a B. So it's the same idea as a tree diagram, but it's not quite as visual for students. So let's look at how we can actually apply these. So if I toss the fair coin 3 times and I record the results, I want to find the following, the sample space that I want to find the event A of getting 2 heads and 1 tail. So if I'm looking at the sample space, I could either use a tree diagram or use the table to generate what would happen in these events. So I could flip 3 heads, I could flip 2 heads and a tail, I could flip heads, tails, then heads again, and so on. So if I want to know the probability of tossing 2 heads and 1 tail, that would be all of the ones that have 2 heads and 1 tail. So that would be 1, 2, 3. So I would have 3 different ways for that to occur out of the total of 9. So if I was looking for the actual probability, out of 8, right? It would be 3 out of 8. If I wanted to know what about having no tails, that only occurs if I get all 3 heads. And then if I wanted heads on the last toss, that would be all of these would fit that criteria. So if I want to continue on with this and I want to roll a fair dice, so different example, similar idea, and I want to find the probability of rolling double sixes. Well, first I'm going to have to figure out all the different outcomes for dice. Now, this is where it gets very difficult to build a tree diagram because there are so many possibilities here. So there are 36 possible rolls that will happen, and if I want to know how many of those give me a 6 and a 6, that's only one of those 36. So the probability then is 1 over 36. So this is going to be something we're going to get a shortcut for. So make sure that you watch all the lectures throughout before you jump into these types of problems in the lab. So if I wanted to do the probability of rolling a sum of a 7 or 11, I'm going to go back into this table and I'm going to add up all of them that would give me a 7 or an 11. And in this case, out of 36 possible rolls, there are 6 ways to get a sum of 7. There are 6 ways to form a sum of 11. Sorry, there are 2 11s out of the 36. So then I would combine them and I would say, well, if I want a probability of rolling a 7, it'd be 6 over 36. If I wanted the probability of a sum of 11, it'd be 2 over 36. And if I wanted to change the wording of the original problem, I could say rolling a sum of 7 or 11 like they did, and that would be 8 over 36 because I would add the 2 probabilities together. Again, I'm not rolling twice. There's not 2 different events happening, but I'm just adding everything that could be a 7 or an 11 to get that 8 over 36. The sample space for the experiment is going to be what's given to you, but the sample space is not uniform, which means the probabilities are not equal of each thing happening. So I make this map of my outcomes, and I look at the probability of rolling a sum or an 11 would be adding the 2 that I found previously, But the difference is here, I've organized my thoughts and my table into something that's a bit more easy to digest, so that I'm looking at the outcomes here for the sums in a table form and not just kind of going willy-nilly on this. Here, if I'm rolling a fair pair of dice, meaning 2, let E be the event of rolling a sum that's an even number, and F be the event of rolling a sum that's a prime number. Then find the probability that it's even or prime. So I'm going to look at my evens, and I've got my outcome table here, evens here, prime numbers here. So my evens are 2, 4, 6, 8, 10, 12. My prime numbers are 3, 5, 7, 11. So I'm wanting to know if either of those happen. So I'm going to add up all those probabilities. So the probability of 2, 4, 6, 8, 10, 12 for my even numbers, plus the probability of my prime, because a number cannot be prime and even, and I get 32 over 36. Alternately, we could work with this and we could do this way, where we would be looking at adding together all the ways to get even numbers, and then adding to that all the ways we can get prime numbers, and you would come out with the same answer. This is another alternate solution where you're using the complement. I don't really suggest using this. I think it's kind of confusing, but if you are someone who the complement really resonates with, you could definitely use this method. If I'm looking at some more of these multi-stage experiments, I have a tree diagram here, which is basically breaking down the information in my paragraph. So I have one colored ball and 2 white balls, which is shown in part A. And then a ball is drawn at random and the color is recorded. So the tree diagram is going to begin to show me what would happen as I start selecting those balls. So let's suppose a ball is drawn at random from the box in the figure and its color is recorded. Then we're replacing it back in. That's important because that's going to affect my sample space. And I'm going to redraw. So if I do the tree diagram for this experiment, it's going to look somewhat similar to what happened with the spinner, but I only have 2 outcomes because I have either the ball is black or the ball is white, so it's not quite as complex. So my probability here, because I'm having distinct events, I'm drawing the first time, I'm drawing the second time, these are 2 distinct events, that means that I'm going to multiply them for the probability because I'm doing a physical action twice. I'm not just saying I want the probability of a black ball or a white ball. I'm saying that I'm drawing one, then drawing the other, and I want the probability of the outcome of that. So that's the multiplication rule for probabilities for tree diagrams, is when I'm actually doing multiple experiments, the probability of an outcome would be the product of the probabilities on the path of that tree diagram. So this is why the drawing the 2 balls is significant, because I'm drawing one by one without replacement. So if I'm doing it one by one without replacement, unlike the other one, once I draw the colored ball from it, there's no chance of getting another colored ball. So that way, the outcome of 2 colored balls is 0, because it can't happen. Then if I'm looking at getting a colored ball and then a white ball, that's going to be, because there were 3 original balls, only one of them was colored, I'm going to do 1/3 times 2 over 2. Same thing here, I had 2 white balls, and then here, so I'm going to complete the multiplication there. Now notice it goes from 2/3 to 1/2, because if I draw a white ball out and I don't replace it, it's a 50-50 shot of getting a colored ball or a white ball. Independent events are going to be when the outcome of one event has no influence on the outcome of a second event. So if 2 coins are flipped and the event is obtained a heads on the first coin and then are obtained as tails on the second coin, I can actually denote these by E1 and E2. So I'm saying these are 2 separate events and they are going to be independent. So if I want to tree diagram this out, I can do that. And then I would multiply the probabilities because they're happening one at a time. And so the way we denote this with our set notation is the probability of the E1, then the E2 would be the multiplication of our probabilities, just like we've been doing in the tree diagram. We're just putting it into formal notation here. So in this figure, I have a box with 11 letters. Some letters are going to be repeated. If I take four letters that are drawn at random one by one without replacement, what is the probability of getting the outcome baby with the letters chosen exactly in the order? So I'm only looking at the tree branch that leads to this outcome. So I'd have to select a B, then an A, then a B, then a Y. So there were two B's in my original image out of 11 total letters. They're out after they're chosen because it's without replacement. So then I have A chosen. There's only one A, but there's now 10 letters because I'm not replacing. There's now 9 letters, and then there's 8 letters. But because I already drew a B, there's only one B left in 1 over 8. So I would multiply each of those independent probabilities to get 2 over 7920, which should be a pretty small percentage. And that should make sense because the probability of coming out with that exact word in that order is going to be pretty low. Now let's look at a different example where I have 3 different boxes. A letter is drawn from box 1 and then it's added to box 2. Then a letter is drawn from box 2 and it's put in box 3. Then a letter is drawn from box 3. What is the probability that that letter thrown from box 3 is a B? So we have a rather complex tree diagram that's happening here. I only need 2 branches because there's only 2 outcomes, getting an A or a B. So I'm looking at getting the A, then I have getting the A because we're putting them back in the other box, and there's 3 letters there. We're putting it into this box, and then there becomes 5 letters there. So to find those probabilities, I'm going to multiply them all together such that the probability of getting what they asked me would be getting a letter B, would be adding all of these probabilities up. Because really, and this is why it's not a multiplication rule, because that comes up a lot. It's not a multiplication rule because ultimately I'm looking at the probability that the third box, the letter is a B. I'm not looking at probability as I draw from one box to the next. I'm only concerned about that final box. That's why you're not multiplying those together. Conditional probabilities are things like given something. There's a given that has to happen. So there's something that has to actually happen. So if I look at what is the probability of rolling a 6 on a fair die if you know the roll is an even number, so that even number has to happen. So if I want to look at the probability of rolling a 6, if I'm given that it's an even number, the probability of that would be 1/6. The probability that it's going to be an even number is a half. So when I do 1/6 divided by 1/2, that's going to give me 1/3. Modeling games could be there are 2 colored marbles and 1 white marble in a box. If you mix the marbles all together and we draw 2 marbles at random without replacement, if they match, Arthur wins. Otherwise, Gwen wins. Does each player have an equal chance of winning? Well, let's take a look. I'm doing multiple draws that I'm finding the probability of, so it's the multiplication rule. And I'm looking at this to see how many outcomes there are. The probability the marbles are the same color is 1/3, because this is going to be 0 here and this is 1/3 up here, while the probability that they are not the same color is 2/3. So the players do not have an equal chance at winning.